Welcome to another edition of Math 20-1. It's the late night edition where we do math and fight crime simultaneously. If you don't know what I'm talking about, then you skip Friday's class, and that's on you. Today, what we're going to do is we're going to do some graphing. So we're going to take a break from all that solving and factoring and multiplying and all that jazz. We are going to graph some reciprocal functions. You're going to notice we skip a few slides. It's just better for this online learning world that we do that. So let's get into it. Reciprocal function. What the heck is a reciprocal function? Well, if we want to remember what a reciprocal function is, you've heard that name before, but you've heard it as reciprocal numbers. I believe a long time ago, you probably would have talked about reciprocal numbers. Oh gosh, I don't remember when. But what a reciprocal number is if you take a regular number, say like 3, the reciprocal of 3. Whoa, can I spell reciprocal? We do math, fight crime, and don't use English properly. The reciprocal of 3 would be 1 divided by 3. That's a 1 divided by 3. Oh, good. We're starting off with bad internet connection. All right. It's going to be a hot class. So if you had the number 3, the reciprocal of 3 is 1 divided by 3. That's reciprocal. It's basically just like flipping fractions all the time. So if you had a number like 13, the reciprocal of 13 would be 1 over 13. And you could technically do it the other way too. So if you had like 1 divided by 5, the reciprocal of 1 divided by 5 would be flipping that fraction to become 5. I mean, remember that all these things are divided by 1, right? That's 3 divided by 1. That's 13 divided by 1. That's 5 divided by 1. All right, so these are all reciprocal numbers. You would have done this at some point in math. I just don't remember when. Okay, today we're going to do reciprocal functions, which is the same kind of idea, except now we're taking functions and we're reciprocating the entire function. So, for example, if we had 2x plus 2, the reciprocal of 2x plus 2 would be 1 divided by 2x plus 2. That's the reciprocal of it, which would look something familiar, right? That from this unit, that looks like a rational expression. So if we reciprocate 2x plus 2, it becomes 1 divided by 2x plus 2. And you could do any set type of function. So if you had x squared plus 3x plus 2, the reciprocal of that function would be 1 divided by x squared plus 3x plus 2. Right? That's a reciprocal function. We're going to graph these things. You already know how to graph those. Right? This is just a linear function and a quadratic function. You know how to graph those things. Today, we're going to learn how to graph the reciprocals. We're going to learn how to graph what happens when they flip upside down. But before we get into that, if you look at those reciprocals, you'll notice that those reciprocal functions are like rational functions, right? And when we did rational functions, we knew there was something called non-permissible values. And those things are going to cause us a bit of an issue when it comes to graphing. So just a reminder of what a non-permissible value is. It's things that cause you to divide by 0. So for instance, if I look at this thing right here, the non-permissible value is what causes me to divide by 0. In this case, it would be that x cannot equal -4. If you look at the middle one, we would have to factor it first, right? So it becomes 1 over x minus 3, x plus 3. And my non-permissible values would be x cannot equal positive or -3, right? These things cause me to divide by 0. If you look at our last one to the right, x could not equal 1 or -3. Those are my non-permissible values. When it comes to graphing these functions, we need to represent these in a graph somehow. So somehow we have to show that x cannot equal those things when you graph them. So how the heck are we going to represent those things graphically? That's the first thing we're going to get into. So when you talk about these things graphically, they're going to create something called an asymptote. So NPVs become asymptotes. And asymptote should be, I think, a new word to you guys. Okay, so that's something that you're like, whoa, I don't think I know what that is. We're going to look at some asymptotes and talk about how to represent them. So if you look, we're going to skip this slide. Skip that slide. Skip that slide. Come to this one. We're going to come right into this example. We're going to talk about asymptotes and how those NPVs happen. So we're going to look at this equation. We have y equals 1 over negative 3 x plus 6. The NPV of that thing would be x cannot equal 2. Right? If you think about that, negative 3 times 2 is 6. Negative 6. Negative 6 plus 6 is 0. That means x cannot equal 2. We need to graph that somehow. That's going to affect our graph. To graph that is called an asymptote. So you're going to draw a line at x cannot equal 2. That line is called an asymptote. So that line would look like this. This dotted line represents x cannot equal 2. It is a vertical asymptote. And when you go to graph these functions, these rational functions right here, your first step will be to draw your asymptotes. These are spots that your graph can't touch. So we're just going to take a minute, pause, so we can catch on what's going on here. So I feel like it's been a little bit of maybe a rough start. We started talking about NPVs. Now we got these things about asymptotes, and it might be like, what the heck is he talking about? So when I graph a function like this that I've got right here, I want to graph this thing. The first thing I have to determine is where my asymptotes are. Asymptotes are lines that you can't cross. They're these dotted lines because my graph can never equal 2, right? That's a non-permissible value. So I need to draw an asymptote to represent that, to say, okay, my graph can never touch this dotted line. So the first spot you always look for asymptotes is your NPVs. I've drawn that. The second spot that you always have an asymptote is your x-axis. So there will always be an asymptote right here. You'll get into why you can't have those values. Again, it has to do with reciprocals, which we'll get into in a bit. It'll always be there. So you don't need to worry about ever wondering if it's there. It'll always exist. You'll never be able to cross the x-axis. And we'll get into a y in a bit. Next year in Math 30-1, that will move. So it is possible that it can move. But for this year, it's always the x-axis. So if I go to graph this thing, the first thing I do is I draw the asymptotes, which are the NPVs, and I draw the x-axis asymptote. The second thing I do is I go to the original function. So this right here, my linear function, it's already drawn for you on your page, is right here. And I'm going to find something on that graph. And what it's called is an invariant point. Invariant points are points on graphs that will be on both that straight line and that overall rational expression or that reciprocal function. Invariant points happen when when y equals 1 or when y equals -1. And we'll talk about why those invariant points exist in a second. So I go to my original function, that red line, right? And I draw little dots on these invariant points. And we'll talk about why those are invariant points in a second. Awesome. Third step to finding the graph of this overall function is now to start reciprocating the original function, or the linear function in this case. Okay, so I'm going to take that straight line that I have, that red line, and I'm going to reciprocate it, because that red line represents -3x plus 6, right? That's what it represents, this straight line right here. And I don't want that as my graph. I want the reciprocal of it, which is 1 over -3x plus 6. So to reciprocate a graph, you take y values That's not how you spell values. Missing my U. You take y values and reciprocate them. So for instance, pick a point on that original graph. I'm going to pick right here. That green point has a y value of 3. If I was to reciprocate that point, the reciprocal of 3 is 1 divided by 3. So that point would come all the way down to here. Notice that the x value is still the same. Both values have an x value of 1. But now I have a y value of 1 divided by 3. So I've reciprocated that point and I'm moving it down there. And I can do this to all the points on this graph. So if I go and I find another one, for instance right here, that point has a y value of 2. If I was to reciprocate that y value of 2, the reciprocal of 2 is 0.5 or 1 over 2, which is right there. And that point has now moved down to 1 over 2. I don't have room to write y equals 1 over 2. But that's where the equals right there, which is 0.5. And I could do this again, right? So if I wanted to do another one, actually I should have left that. Just for now. Let's do another one. Let's find this point right here. That has a y value of 5. If I reciprocate 5, it would become 1 over 5, which if you put in your calculator is 0.2. So that point would come way down to here at y equals 1 over 5. Right? This point is going way down to here. And you'll notice that we're making a bit of a trend. Okay, and that trend is that these big points are getting lower and lower and lower. So if I took another one up here, say y equals, I don't know, that would probably be 6. 1 over 6 would be really close down here. And I would keep getting these points that are going to get closer and closer to that asymptote, but they'll never actually touch that asymptote. If I was to connect these dots, my graph would look like this. And it makes that little curve. That green curve I just drew. And I got that green curve by doing all of those reciprocals and noticing the trend. So I'm just going to do a little bit better of a job there. And that line will go as close as it can to that asymptote, but it'll never touch that asymptote. The reason why is because I'll never get 0. I'll never get a y value of 0. I'll get 1 divided by 1,000,000, right? But 1 divided by 1,000,000 technically isn't 0. It's just really close to 0. It's like 0.000001. I'll never get a number, a y value, that reciprocates to become 0. It's not possible. That's why I never actually get to that dotted line. I just get really close to it. And this curve, this green curve that I've drawn, it actually keeps going. So I'm going to erase those reciprocals that I've drawn. And I'm going to show you that this curve actually goes upwards too. So if you were to take some points that are down along here. So for instance, let's take this spot right here. Let's pretend that's y equals 1 over 2, which is 0.5. The reciprocal of 1 over 2 means that that point from that original graph would reciprocate up to here at y equals 2. And let's go a little bit smaller. Let's pretend there's a point right here at y equals 1 over 4. The reciprocal of 1 over 4 would become y equals 4. And you'll notice that this green line that I'm drawing, it'll actually continue its way up too. And it'll get really close to that asymptote, but again, it will never actually reach that point. The reason it'll never reach that dotted line is because I don't have a dot right here that can reciprocate. That would be x equals 2, and we know that in our function, x wasn't allowed to equal 2. The reason it's not allowed to equal 2 on a graph is because that has a y value of 0, and the reciprocal of 0 would be 1 divided by 0, which is not allowed. That's why you get these things called asymptotes. They're what happens when you divide by 0. That curvy line is the first part of our graph, of our reciprocal function. I'm going to erase all these little points that help show that. That's like the mathy side of how to get those things. Oh, sorry, there's one more thing I want to talk about before I move on to more. What happens at that yellow dot that we have? So if you look at that yellow dot, we got this point. It was at y equals 1. If you were to reciprocate 1, it becomes 1 over 1, which is 1. It doesn't move. That's why this thing is an invariant point. Because when you reciprocate 1, 1 becomes 1 divided by 1, which is the same thing. So this dot at y equals 1 is on both graphs. It's on my curvy green graph, and it's on my straight linear red graph. That's how we got those invariant points, because the reciprocal of 1 is 1. Okay, that's like the mathy side of how to get these things. To reciprocate in another way. And I won't spend too much time anymore going over like the mathy side of it. To graph these things a little easier, what you're going to do is you're going to find your invariant point on that red graph, that straight line, which I've already labeled for you. All right, I've labeled one of them right here. That's my invariant point. You are going to put your pencil on that invariant point, and you are going to start to draw a line towards one of your asymptotes. It doesn't matter which one you go towards. I'm going to go up first, and I'm going to go towards this asymptote. And as I approach that asymptote, I'm going to curve, and then I'm going to go right against that asymptote like that, and then put an arrow on it. Like that. I'm then going to go back to my invariant point. I'm going to do the same thing towards my other asymptote. So now I'm going to go left towards this asymptote. As I run up to that asymptote, I go right beside it, and then I put an arrow on the end. I like to picture these asymptotes as like fences, right? And my graph is like a little dog pathway. He would run right towards the fence, and then he'd just run all the way along the fence. He can't actually get through the fence. So that's what I picture those asymptotes as. It's like a fence line. That green graph that we just drew, that is 1 over negative 3x plus 6. The green graph, that green bendy line. If you were to look at just that bendy line on your graphing calculator, it would look like this. That's what our green graph would look like on your graphing calculator. And it would probably also draw the asymptotes. I don't think it draws the horizontal one. But that is what we just graphed. You won't actually graph these in your calculator. You're going to graph everything by hand, because it's actually easier than trying to read your calculator's graph. All right, I know. So don't feel like, I shouldn't say don't feel lost. You can definitely feel lost, because we're going to spend 3 days basically graphing reciprocal functions. And the first time you see me graph one of those, you are like, what did he just do? And I hope you haven't been like pausing and rewinding too much before you get to this little lecture. It's okay to be lost. It's okay. It will come. Trust me. We're going to do this. You're going to notice it's a pattern. And then once you get that pattern, it's going to roll. And you're going to get very good at graphing these things. Every single year, we get really good at graphing them. But every single year, the first day of it is like, what did he just do? Right? So please pop into the classroom and ask me questions as you see this next example. So you can be like, wait a minute, how is he getting those things? But I'm going to go through these 3 steps again. So I'm going to do asymptotes, invariant points, and reciprocating so that you can see what it looks like. And we'll do a couple together, and then you can practice. And you need to come ask me for help, okay? Because once you figure it out and you ask 1 or 2 questions, trust me, it gets easy. But you have to ask those questions. Let's look at another example. So our goal is to graph this thing right here. It says sketch the graph of y equals 1 over x minus 3. To graph this, you need to have the original graph, like the reciprocal, which is x minus 3. They've drawn it for you. So this thing right here, that is y equals x minus 3. That's the straight line graph. That's all that is. Our goal now is to graph the reciprocal of that thing, which would be 1 over x minus 3. To be able to do that, we have to follow 3 steps. The first step is to draw your asymptotes. Asymptotes are lines you cannot cross. The first asymptotes you go and you draw are the ones that are your NPVs. So if you look at this function, the NPV would be x cannot equal 3. So you go and you draw a line at x cannot equal 3. So you draw a line right there. And you always do your asymptotes dotted. Remember, these are lines that your graph won't be able to cross. It's like boundaries. Your second asymptote is always your x-axis. So right there. Perfect. You'll also notice, just for fun, your NPVs, if you look at your linear function or the original function, it's also the x-intercepts. Right, so it just so happens that NPVs are x-intercepts of the original thing, if you were to graph the other side of it. Okay, second job. To every one of these questions is to label invariant points. These are points that your graph will have in common with the line, the x minus 3, and the reciprocal 1 divided by x minus 3. They always happen in 2 places. The first place is at y equals 1. So if you look, y equals 1 is here. So on the original function, it's this dot right there. That's y equals 1. The second spot invariant points always happen is at y equals negative 1. So I go y equals negative 1 right here. So on the graph, that would be this spot right here. Always draw your invariant points. The third step is to reciprocate. And remember, you're reciprocating y values. To reciprocate, to actually draw out the graph, you're going to put your pencil on one of your invariant points. I'm going to put my pencil on this one. And then you are going to move towards one of your asymptotes, and then you're going to run beside your asymptote as if like a dog running beside a fence. So I'm going to go up and then along this asymptote like that. And then always put an arrow on it, because that graph will go forever along that asymptote line. Go back to your invariant point, and I'll go the other direction, like that. And notice that I'm running up to my asymptote, up to my boundary, then I put an arrow on it, like that. And I never crossed that dotted line. Now would be a good time to pause and see if you can do the other part of this graph, because there's another invariant point, which means you have to do another little reciprocal, little curvy graph. So maybe pause, see if you can draw the rest of this graph. Okay. Hopefully you gave it a try. So to draw the rest of this, I put my pencil on my invariant point, and I go towards my asymptote, and then I run beside it. So I'm going to go left and then towards my asymptote and then run alongside it. And I put an arrow on it. Then I go the other direction towards the other asymptote. So now I'm going to go down towards this asymptote like that. And again, I put an arrow on it to show that I'll run beside that fence forever. That red graph is y equals 1 divided by x minus 3. The red graph is. The blue graph is x minus 3. The green lines are my asymptotes. If you can follow that pattern, draw asymptotes, draw invariant points, and then reciprocate, you'll be able to do this. Okay. Let's try the other direction. This is weird. It's got both graphs there for you. So the red graph here, the red graph is y equals 1 divided by something. We don't know what it is. The question wants us, what is the equation of f of x? They want us to figure out what f of x equals. To be able to figure out what f of x was, we're going to try to draw it. Okay, and the way we're going to draw it is by doing the reciprocal backwards. Okay, so the first thing that we're going to do is we're going to look at the asymptote. Because that asymptote is going to tell us what the NPV would have been. If you look at this, the asymptote is going through 2. That tells me that the NPV was x cannot equal 2, which means the original graph had an x-intercept of 2. The next thing I'm going to do is I'm going to label my invariant points. My invariant points are when y equals 1 and y equals -1. And by getting those invariant points, which would be right here and right here, I would then be able to create a straight line. Let me go up a little bit. Through those 3 points that I have. So I can go through that x-intercept, which was my asymptote, and I can go through my 2 invariant points to create that yellow line that I have right there. The reason that's useful is now I know the type of equation that f of x was. F of x is linear. I mean, I've drawn it, right? This thing is f of x. And we know that linear equations are y equals mx plus b. So if I wanted to find what that linear value was, I would have to go to that function and find my m value, which is my slope, and my b value, which is my y-intercept. On this graph, my slope, I want to find 2 points that work out nicely on this graph. I'm going to pick right here and right here. My rise is -2. My run is 1. That means my slope is negative 2 over 1, or just negative 2. My b value is my y-intercept. This is my y-intercept. It's at y equals 4. So that means my b value is 4. That means I can create my equation now. My equation is y equals negative 2x plus 4. That is what f of x would have been. So f of x is negative 2x plus 4. That means that original red graph that they had would have been 1 divided by negative 2x plus 4. Now that straight line was drawn for you already, so it's already on your page, but I showed you how we can work backwards from a curved graph to get that straight graph. That's how I got that straight line. All right, here's another one here. Again, you'll notice things in common, right? So we have our asymptote right there is that x-axis. We have invariant points, which are at 1 and negative 1, which created this nice straight line for us. That would be what's on the bottom of an equation. So that would be f of x, which we know is linear. It's a straight line. So f of x would be y equals mx plus b. To find my m value, you find 2 points on that straight line. Let's say this one right here looks pretty good, and this one up here. So I would say it goes 1, 2, 3, 4, 5. It was a rise of 5 and a run of 1. So 5 divided by 1 is your m value, which is just 5. My b value, which is your y-intercept, would be right there at y equals 3. So my b value is 3. That means f of x, which is that straight line, would be y equals 5x plus 3. The reciprocal of that thing would be 1 over f of x, and that's what would create those red curved lines, which would be 1 over 5x plus 3. That's the red one. Actually, I should do that in red since then it all kind of matches color-wise. My internet is making everything connect. There we go. That's what the red graph would have been. Okay, from today. I know today is confusing. I know that, right? That's why we're going to do 3 days on literally this exact same stuff. We're going to spend 3 days doing this. So it will come along. I want you to try to go practice. The thing that really is going to matter is being able to do this stuff. So this question we did together, where we had that straight line and then we reciprocated it. That is like the skill you're going to want to be able to be good at. In your practice booklet, there should be a couple questions where you can practice that skill of sketching. Okay. I had the straight lines already drawn for me on this question, right? But the straight line just came from the bottom of my fraction, x minus 3. And that's easy enough to sketch because it's just a straight line. The other stuff was me sketching by doing an asymptote, invariant point, reciprocate, right? And then actually drawing those curved lines. I know it's hard. I know today's weird and confusing. Tomorrow will be a little less confusing as we go through it again. And then the day after that will hopefully be a little bit less confusing again as we draw these graphs. And usually people rock the test questions on reciprocal graphs. It just takes a few days. And once it clicks, trust me, it's going to be good. It'll be okay. All right. If you have any questions, come find me, right? I'm hanging out. I'm always looking for one-on-one help. Those of you who've been asking for it, I think it's helping, right? It seems at least it's working for those who've been asking for it. So keep asking. Don't be shy. We have 1 week left and then we get Christmas break. So go hard this week. And then after Christmas, we'll come back with some trig and hopefully life will be okay. All right. Talk to y'all soon. Take care of yourselves.